Alright, so I'm going to run us through this problem real quick. It's the question to number 17 on the WebWork for line integrals. So this is where they give us a vector field, but with no like r. So r is supposed to be the equation of these lines. This one's C1, this one's C2. Just going to walk us through how to do these. So since we don't have dr, what we have to find instead is dt and dy. So the equation would instead look like that'd be f. So I'll just plug in the x plus y. So we got xi plus yi, and it's going to be times dxi plus dyj. So to find dx and dy, we just take the derivative of these that they give us. So we have x equals t. And this one's simple enough because then just dx equals dt. So that one's pretty easy. And we just do the same thing again. So we get dy equals 2t dt. And then we have to make this whole thing in terms of t. So we take this vector field, and we just plug in for x and y. We just plug in for x and y the values that they give us for this. So our equation, or our integral now looks like, let's see, it just says 0 to 5. So from 0 to 5, so we get t I plus, what is it, t squared j times we get dti plus 2t dt. So then we do that out again. So now we do the dot product, and we just get t for that, and we get plus, because it's just 1 times t, and then we got 2t times t squared, so we get 2t to the third, and that's all dt. And that's a pretty easy integral to solve. So then we just get t squared over 2 plus, let's see, so we get t fourth over 2, because it's 2 divided by 4 equals 1/2. And then that's from 0 to 5. And since it's 0, and everything has a t in it, we don't got to worry about the second part. So once you plug in the values for that, you get the work is 325 units of work done by the vector field on this parabola. So that's the first part. Pretty simple, not too hard. So then we just do, just make sure I'm still recording. Alright, so I'm just going to walk us through this next part. So it's pretty much the same approach again, except for we have different bounds and then different values for x and t. So just to have our equation again, it'd be C2, then it would be x, let's see, oh, my bad, be xi plus yj times dxi plus dyj. So again, we have to find our dx and dy. So we do, let's see, x equals 5t squared. Take the derivative of that, we get dx equals 10t. We do the same thing again. Y equals 25t squared. So we get dy equals 50t. And now we just plug in for the values that we have. So this time we go from 0 to 1, and we say that x is now 5t squared I plus 25t squared j. That's all being dot product by, let's see, so we got the dx now, which is 10t I. Should have put that underneath, my bad. And then we have our dy, should be plus our dy, which is 50t. So we got 50t. No, that's all to, oh, my bad, one thing I forgot to add. There's dt's behind all of these. Right, I think. Hold up. Yeah, my bad, I forgot to add that part in. There's, oh yeah, I put it up there. Okay. dt's. And this is all dt at the end. So now we just do the cross product. These keeping it from 0 to 1. So we get 5t squared times 10t. So we get 50t to the third. And we get 25t squared times 50t is, let's see, 1250 t, and that's also squared. And dt, you can combine those terms. So we get 0 to 1, and we get 1300 t to the third dt. That's also a pretty easy thing to integrate. So we just, then we end up getting, let's see, 1300 divided by 4, pretty sure, let me just double check, it's 325, yep. So we get 325 t to the fourth, and that's from 0 to 1. And look, it looks pretty similar to our last value. After we do it, we don't got to worry about the 0, and it's just a 1. Anything to the power of 1 is just 1. So then we get 300, oh geez, I can't do 3's, 325 units of work. So sometimes it's honestly easier for us when we don't have a, when R is not given and we just have the C1 and C2. It seems to make the problem a lot more simpler, easier to handle. So something that you can do is you can check it in like CalcPlot just to make sure that these kind of are almost the same area in a sense. It was kind of weird how it's different equations, different bounds, and then somehow they end up having the same like work. So one thing I do is we can check the CalcPlot. So first we just have the vector field. Just put in that value. It's like the most simplest vector field that we can be given. You know, and we can tell it's conservative too just by like looking at it. So for the first one, this is for that parabola, and 5 is about right here. And you can kind of tell it goes up for a bit, but it says, where is it? It says that the curves go from 0 to 0 to 5 to 25. So you can tell that that value goes pretty high up. You can kind of just see the area from there, and then if you do that straight line segment from 0 to 1, you can kind of see that they're very, very similar, at least how like they look so far. So you can kind of tell that like the area is going to be like around the same value. So there's nothing to worry about there if you get those same values. I mean, I don't know how often it will happen when we're giving two different C's and then we get the same value for what the units of work are, but yeah, I guess that's pretty much it for this problem. It's pretty just straightforward. You know, when we're not given the R, we just go through with the line length we're given, find dx, dy, plug them in, plug in the values for x and y into the vector field, and then do the dot product, and then take the integral, and just do the same again. So it's not too simple. I mean, it's not too difficult. So